So this is an example of extraction you might do if you're trying to extract a metal ion from an aqueous phase using an organic phase, and we can do that by complexing. So quite often ligands, the neutral form of the ligand dissolves well in an organic phase. So what we're going to do is extract it into an aqueous phase where it will ionize as a weak acid and then bind to our metal ion. So this is actually our analyte here, the metal ion. We have a ligand, a neutral ligand in the organic phase that will partition into the aqueous phase, then acts as an acid, so it will ionize. So you get anion form of the ligand, which will bind to a metal to form a neutral complex, metal ligand complex, that then will partition back into the organic phase. Using a liquid-liquid extraction to extract a metal ion from the aqueous phase by forming a complex means that we have to take into account a couple of different equilibria. And again, the distribution ratio is not going to be equal to the partition coefficient, so we have to calculate that. And we have this kind of big ugly equation in order to do that, where the distribution ratio is equal to beta, which is the formation constant for forming the complex, multiplied by the partition coefficient for the complex, times the acid dissociation constant to the power n, where n is the number of ligand ions which are going to bind to the metal. So in the aqueous phase we have a number of ligand ions in order to get a neutral complex, and then it's going to form the complex, which is the metal ligand, or some number of ligand molecules. So n here is the number of ligands that we need. So we also need to know the concentration of the ligand, again to the power n, and divide that by the the partition coefficient of the ligand to the power n times the concentration of the acid, because there's also a Ka involved, again to the power n, and then we have to add in the complex formation of the formation constant for the complex, Ka to the power n, and again the concentration of the neutral form of the ligand to the power n. So we have a lot of terms in here. As an example, let's use the complex formation constant as 1 times 10 to the 15. These tend to be pretty strong, strongly product favored. And we'll use Ka again as 1.7 times 10 to the minus 5. Let's say the concentration of the complex is 1 times 10 to the minus 6 molar. And we have a pH of pH 5. So again, the H3O plus concentration is going to be 1 times 10 to the minus 5. And I think we have everything. N in this case we're going to say is 2. So we have 2 ligand molecules to every metal ion. And if we have, the only other thing we need is the distribution or the partition coefficient for the complex, and we're going to say that is 100, and the distribution coefficient for a ligand molecule we're going to use 7.5. So I think we have everything now. You just have to put it into the equation and solve. And when you do that, we end up with the distribution ratio being equal to 1 times 10 to the 15 times 100 times Ka, which is 1.7 times 10 to the minus 5 squared, times the concentration squared, so 1 times 10 to the minus 6 molar squared. And divide that whole thing by 7.5 times 1 times 10 to the minus 5 squared. And we're going to add 1 times 10 to the to the positive 15, the complex formation constant, times 1.7 times 10 to the minus 5 squared, and 1 times 10 to the minus 6 again squared. Do that thing out, and if I've done my math right, you should get an answer of 99.7 for the distribution ratio. Once we have that, we can just put it into our same equation again. So we need to know volumes if we want to know the extraction efficiency. So we'll use the same volume. Volume of organic is 50 mils. The volume of the aqueous phase is 30 mils. So Q for just a single extraction is going to be 30 over a value of D, which is 99.7 times 50. And then we'll add that to 30. And you get an answer of 0.0060. Remember, this is the fraction left in the aqueous phase. So that's a pretty low number. We do 1 minus that and multiply by 100. We end up with the extraction efficiency, which in this case is 99.4%.